in an experiment.
We don't know yet.
Why is light so far?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This week, capturing contrails at 30,000 feet.
And what we can learn from fakery in science. I'm Shamini Bandel.
And I'm Benjamin Thompson. If it's a sunny day and you look up into the sky, it's pretty likely you'll see an aeroplane overhead. And if this plane is flying at a high enough altitude, you might see a long white plume behind it. These plumes are known as contrails, and they're made up of ice crystals. They're formed when water in the atmosphere condenses and freezes around soot particles produced by a plane's engine. And contrails can have a significant climate impact. The ice crystals can spread out to form contrail clouds. Now, these might only last a few hours, but they can trap heat, preventing it from escaping Earth. Estimates suggest that the climate effects of contrails almost equal those of the carbon dioxide emissions produced by the aviation industry. As part of efforts to lower CO2 emissions, an increasing number of planes are being fitted with what are known as lean burn engines. These are more fuel efficient than existing rich burn engines, but their effects on contrail formation wasn't well understood. That looks to be changing though, thanks to an adventurous study published in Nature this week. I spoke to Christiane Voigt, one of the members of the team, to find out more about it. So there was a lot of uncertainty about the contrails formed by lean burn engines and how many ice crystals they may contain. And trying to figure that out almost becomes an action movie then, where you chased an aeroplane of a type used in commercial flight with another research plane to see what contrails were coming out. I mean, that can't have been an easy thing to organise. Tell me about your experimental setup.
Yeah, so you have to put two aircraft into the air. We worked closely also with industry because they provided the leading aircraft, also with the engine manufacturer because they provided the engine. And all that had to align with our measurements with the research aircraft. And we had to lift all these aircraft together to perform this very challenging measurements. So imagine if you would fly in the air in 10-kilometer altitude at 150 meters per second, 50 meters behind another aircraft, which is also flying very, very fast. When you get into the exhaust plume, the exhaust pushes back our research aircraft. It's very, very shaky. It's like when a hammer hammers on the aircraft in a very, very frequent way. Then we get out again, we get into the plume again, make 40-second measurements, get out again, and it's really an adventure.
And for folk listening then who maybe don't get a sense of this, you really are so close, like 40, 50 meters behind the lead plane, almost within touching distance, I guess. And I've seen a picture of the research plane, the Falcon. It's a fairly unassuming looking thing. It looks a bit like a private jet style aeroplane, but it has this long protuberance that almost looks like a narwhal, sort of a lance-like structure sticking out of its nose. And this is what's sniffing the air. I mean, what's it like to be inside this plane?
So what you see in those figures is the nose boom of the Falcon for atmospheric wind measurements, to measure the turbulence also within these exhaust and of the atmosphere. And the aircraft is packed with instruments. In racks, we have about 4 operators operating the instruments during the flight, having all this exciting experience. I'm organizing those campaigns, but sometimes I have the chance to also take part in the flights. And it's a very hard job to be sitting there, but we are doing it because we are very motivated and we want to change the world a bit, make the world a bit more clean.
And here's a question. Do you get airsick?
So when I sit in this aircraft, it's very good to know that these measurement sequences have a limited time. So when knowing this, then it's okay. But after those flights, I did some normal passenger flights and we went into turbulence. And I really thought, well, That's no problem. The aircraft can stand it. The pilots are very experienced. So turbulence for normal passenger aircraft is not a problem anymore.
So you have this setup then, and as I understand it, the commercial lead plane that you were testing, it could change its engine to run on this lean burn combustion or on a more regular rich burn. Now, you showed that the lean burn produced a lot fewer soot particles, but the lean burn engines still produced contrails. What did your research suggest was going on? How were these contrails still forming when there was much less soot present?
So that was also astonishing for us, that despite the very large reduction in soot particle emissions, we still found significant amounts of ice crystal numbers. So it was a question, what could have led to the formation of these contrails? Soot particles couldn't be the cause, but what we saw is very, very tiny liquid particles. We call them volatile particles. They exist at very high numbers. And normally those liquid particles form in lower concentrations because the vapors are taken up by the larger soot particles. But as the soot particles are reduced, we could show that those liquid particles have the ability to form contrail ice crystals for these new lean burn engines compared to the rich burning engine.
So rather than these volatile liquid particles sort of being absorbed or sucked up by the soot and then the nucleation process that forms ice crystals happening, it was happening on its own in the absence of the soot being there.
Yes.
And was this a surprise?
Actually, it was predicted by theory that sulfate aerosol could form those volatile particles and they might lead to contrail ice formation. But it had not been experimentally shown in the atmosphere that this would happen. Also, it was a question how many of those sulfate aerosol would really form ice crystals, and theory predicted a 4 orders of magnitude range.
And so where did it fall then?
So for conventional fuels, we measured about the same number of ice crystals for these new lean burn engines compared to the rich burning engine.
So the engine type might not necessarily make a huge difference to contrail formation, but there is another factor that you looked at, and that's the fuel that the engines used. How did different fuel types affect the contrails?
So now we had a specific look on the sulfur content within the fuel, and we found out for the measurements that reducing the fuel sulfur content by a significant amount then led to a significant reduction in contrail ice crystals. So now it seems that in addition to this lean burning engines, when also using fuels with a lower sulfur content, that could significantly lower the ice crystal numbers and contrails, again by an order of magnitude, which is a lot actually. Normally in physics, if we can reduce by a few percent, we are already happy. But a reduction by an order of magnitude, that is large.
So it seems that based on the evidence you're showing in this paper, engine change alone isn't enough to reduce contrail formation, but it's this combination that you think will do the business.
Yes, I would agree. So the combination of the engine, the combustor technology, and the fuel with a reduced sulfur content, but also reduced aromatic content, because the aromatics are the precursors for the soot particles. So if both is reduced, then that could pave the way for future cleaner aviation or contrails with a lower climate impact. But of course, something remains. For fuels with almost no sulfur, we call them ultra low sulfur fuels. Some other particles might get activated, and that we found out by comparing our measurements with the models, and those particles might come from the lubrication oil released at a certain position within the engine. That is now not a fuel component, and we found out that that also has an effect and that further changes might be needed in future.
And your paper is out now. What do you hope it gets used for? What do you want these results to do ultimately?
I think it's really very helpful to inform aviation industry on the further improvements of the engine architecture, also with respect to the fuel compositions to reduce the climate impact from contrails. And then there's another point actually also to the scientific community. So right now, current climate models, they just calculate that contrails form on the soot particles. They do not take into account those volatile particles. And there's already about 20% flight kilometers flown in the actual fleets. They have these lean burning engines. So it seems that the climate impact from aviation is underestimated because this process is not taken into account. So we also encourage to adjust the contrail climate modeling and to adjust the climate effects from aviation in total.
And obviously this was a difficult experiment to set up. What questions were left on the table, do you think, and what's left to understand?
I think we have many limitations. For example, that was the first measurements with one engine type and one aircraft and set of fuels in a specific atmospheric condition. So of course we need more measurements. But also what we, for example, do not cover right now, we have just measured the initial contrail formation up to 2 minutes of contrail age. We have not measured how the contrail spreads out and how those changes will affect the climate. That is also a topic we have not assessed yet, and that should be assessed also in future.
So more time in the aeroplane for you then, by the sounds of things.
Yes, with many colleagues and eventually telling more on the exciting science that we do here.
Christiane Voigt from the German Aerospace Centre and the Johannes Gutenberg University Mainz there. To read the team's paper, look out for a link in the show notes.
Coming up, a discussion of what fakes are in science and what we can learn from them. Right now, though, it's time for the research highlights with Dan Fox.
A Soviet submarine lying at the bottom of the Norwegian Sea is leaking radiation, but not enough to be hazardous, according to research. In 1989, the Komsomolets burst into flames and sank, taking with it the plutonium in its nuclear reactor and reportedly 2 nuclear torpedo warheads. In 2019, researchers analysed water near the submarine using a remotely controlled submersible. They found elevated levels of radioactive strontium and cesium emanating from a ventilation pipe. These radioactive materials were quickly diluted to low levels in the water around the submarine. They also found signs that the nuclear material in the reactor is corroding. The team detected radioactive cesium in some corals, anemones and sponges growing directly on the submarine, but the levels are not thought to be high enough to harm these organisms. Deep dive into that research in the Proceedings of the National Academy of Sciences. Forever chemicals that don't break down in the environment have reached even the ends of the Earth. Now researchers have more insight into the levels of these pollutants in Antarctica thanks to new observations taken across the continent's ice sheet. Per- and polyfluoroalkyl substances, or PFASs, are used in a wide range of consumer products. Researchers analysed PFAS data gathered during a 1,200-kilometre trek made by a polar expedition team from the coast to Dome A, the highest point in East Antarctica. PFAS concentrations rose along the path from the coast to Dome A. There, the year-by-year accumulation of snow layers captured the introduction and phasing out of different chemicals over time. Gathering more data on Southern Hemisphere PFAS emissions could help to pinpoint the sources of this pollution. You can find that research in Science Advances.
It's April the 1st, and on this day of fools, you might be used to seeing some jokes, some pranks that will most likely elicit an eye roll, if not a chuckle. But today has also been turned into an opportunity to look at something a little more intellectual, and which science has a keen interest in: the nature of truth. Today, we're talking about April Fakes Day, an event in which a sociologist and a group of museums have been working to engage with the public on fakery, the impacts of things like forgeries, artificially generated images and fraudsters. And they've been asking if these kinds of fakes can have value. This year, they've turned their fakery lens onto science. Reporter Nick Petrich-Howe spoke to Patricia Kingori, the University of Oxford sociologist who started this initiative, and spoke to her about what fakes are, what truth is, and the bad and good that can be done to science by fakery. He started by asking her to explain a bit more about April Fakes Day.
I had this idea that it would be really great to have people from lots of different backgrounds engage with the question of what is a fake. I think it's one of those questions that lots of people feel that they know and have a very unquestioned relationship with it, but actually more time you spend thinking about how would you identify a fake, who gets to say that something's fake, the more interesting the question becomes.
And this year, the focus is on fake science. What sorts of things were you thinking of including in this?
So what we're doing this year is looking specifically at ideas around science and pseudoscience and what we can learn from paying attention to that. So in the past, what we've had is fake objects. Last year, we had fake people. And this year, we're looking specifically at fake science and trying to really ask questions around what can we learn by paying attention to these fakes, and how can we think more creatively and lead with our kind of curiosity around what is fake or real science.
And when you say fake science, is this artificially generated images of scientific data? Is this, papers that have been produced by someone who's never done the research, that sort of thing? What sorts of things do you encompass in that definition of fake science?
We've got the Natural History Museum, which is looking at objects that they've had which are now known to be fake. So animals that were invented or created. The Victorians had a big passion for inventing animals that didn't actually exist. And so they're going to be looking at and questioning some of these objects. So, for example, they're going to be showing images of a platypus, which nobody at the time thought was a real object. And they had assigned this to be fake, although actually the platypuses do exist, but their features were such that no one at the time thought that they were real. So I'm also really interested in troubling the confidence of how we get to decide that something is real or fake. We're also doing some work around how can we spot the difference between real and fake science. So looking at scientific evidence and authority and how this can be sort of misinterpreted and manipulated.
It sounds like there's a lot going on here, and your work focuses on global health. Are there places where this work sort of intersects with your research?
Yes, I think the fakes really represent lots of ethical questions, which I think is really worth us spending time and thinking about. So one case in particular in Western Kenya about 10 years ago of a doctor who was really successful and was doing lots and lots of surgery and doing really, really well, and was about to be given an award when they found that he had absolutely no qualifications. And so this is a fake doctor, but actually it was only the fact that he had done so well that had highlighted the fact that he didn't have the necessary qualifications. And so what do we do in a situation like that, especially in context where there aren't enough doctors?
Yeah, I mean, when I was looking into this, I came across one of the videos you did with a forger of paintings, and it was a very interesting video, and it sort of raises the intriguing question of, is there any actual value to this? These are fake paintings, but is there real value to this? Do you think this sort of line of thinking could be something applied to science as well?
Yes, I mean, I think that there's something really interesting around the policing of these boundaries. And so the person who you were talking about, who I interviewed last year for the Fakers focus on April Fakes Day, was the artist John Mayat. And he produced over 200 paintings, and only 40 so far have been detected and collected by the Metropolitan Police. So he's got over 160 of these paintings that are in circulation in galleries, not only in the UK, but all over the world, that we are able to go and look at and enjoy, thinking that they're the real thing. So then the question then becomes, under what circumstances are fakes acceptable? And we see this, that technology can be really helpful in providing us with replicas and alternatives to the real thing. And so then the question then becomes, are those things fake? Do we only ever think about the fake in relation to deception, in relation to, for example, science? So if we have a rendering or a replica of something, if that's disclosed, is that okay? Is the problem that we have only exists with the fake when we don't know that it isn't the real thing.
Yeah, it's an interesting reframing because, my background as a journalist and as a science journalist, like when I encounter fakes in science, I'm used to thinking of it as just a bad thing. Like these are people trying to make out that papers said things that they didn't, or images say things that they didn't. That's sort of the way I'm used to encountering it. So it's an interesting way to approach it.
Thank you. And I think there's also, one of the pieces of work that I've done, which are on these academic writers for hire in Kenya and the fake essay industry. The very nature of calling something fake essay industry suggests that they're fake, but actually they're the ones that's producing real essays, real theses, real publications, real academic outputs, but none of that's credited to them. And students and academics in the global north are taking credit for that. So their argument is that they're not the fake, they're the real, and the academics and the students in the global north are the fake. So paying attention to where the fake exists and where we suspect the fakes exist is also really fascinating as well to think about.
And, ultimately, I guess this kind of comes down to what is truth, which in some senses is what science is trying to discern, like what is truth. So what do you hope to get out of this? Do you want to understand what truth is?
I think I really want to understand the relationship that power has in deciding what truth is, and that actually if we make this process more transparent, we could all have much greater say in what truth is. At the moment, I think truth and the decision around what's real has historically and currently been in the hands of very few people. And I think that we can have that process be more open and transparent, and also be just more honest about areas where we just don't know and where we need more information. And I think the best of science does that. And the best of science says we don't know. But I think there's also elements where things are hidden and there isn't open discussions actually about what we don't know. And I think that there's always room for more of those kinds of discussions.
But there's almost a tension there, though, because there are bad actors who would willfully spread misinformation, disinformation, and then there are authorities that may be trying to project the truth. So do you sense that there is a tension there and how we can sort of weave our way through that?
I think one of the things that we've learned, certainly from things like COVID, for example, is actually the public are much more receptive to just being told that we just don't know and we're uncertain. Bad actors are able to really capitalize uncertainty and manipulate that if scientists aren't open about what they don't know. So actually, I think what we've learned from that is that being open about things that we don't know and uncertainty is often the way to gain more trust and to gain much more buy-in into science. I think when we paper over the areas of uncertainty, or at least present them in much more confident ways than they are, that's where people often can accuse others of being fake or at least not being real. I think we're much more receptive now to understanding that things are really complicated and that we don't know everything. I think the public are much more open to that, and I think we can start having many more discussions around that now.
Patricia, thank you so much for your time.
Thank you.
That was Patricia Kingori from the University of Oxford here in the UK. For more April Fakery, check out the show notes for some links.
And that's all for this time. But before we go, a quick update on a question, Shamini, that you posed to listeners at the end of last Friday's show.
That's right. We were talking about clones deteriorating over time. And I said, what is the sci-fi film show franchise that has that as a plot line? And quite a few people wrote in. I think the most popular answer we got was the film Multiplicity, which I hadn't seen, but I did watch a trailer for. And a guy clones himself so that he's better able to handle all the stresses of life. And it goes hilariously wrong very quickly. But one person did actually write to me and say, is it this Star Trek Next Generation episode? And I was like, I think that is the one I was thinking of. I'm such a Star Trek nerd that might have been the one in my head when I said it. So thank you all so much for your sci-fi education this week.
And I think it's always safe to say with us, you can assume it's probably Star Trek related.
Yeah.
And the best one, which is The Next Generation.
No, absolutely wrong.
But of course, we don't have time to debate that today, or in fact ever really. But if you'd like to reach out to us listeners, we're on social media at Nature Podcast, or you can send an email to podcast@nature.com. I'm Benjamin Thompson.
And I'm Shamini Bundell. Thanks for listening.